Hello, I'm Joe Hamaker, and in this presentation, I'll be discussing estimating the cost of hypersonic vehicles. First, a word about me. I'm the Director of DoD and NASA programs at Gallerath Federal. Formerly, I directed cost at NASA, and I have over 40 years of experience with cost estimating and analysis. My email address is at the bottom of the chart, jhamaker@gallerath.com. Now, this presentation is meant to be a bit of a novel look at estimating the cost of hypersonic vehicles. It might surprise you that while hypersonics is a very current topic, there have been quite a few hypersonic vehicles in the past, and that we can gather the cost and technical data to make a cost model. So my purpose here is to pique your interest in the subject of estimating the cost of hypersonic vehicles, and I'll close with a word on a more rigorous approach than the one I'm presenting here today. Now, I'll be covering a lot of complicated material quickly, so feel free to contact me if you'd like to delve into some of these subjects in more detail. Wikipedia defines hypersonic flight as flight through the atmosphere at speeds above Mach 5. So heat is going to be a big cost driver, obviously. It forces hypersonic vehicles to use advanced materials, to have very capable thermal protection systems, and to harden their equipment and electronics against the environment. Beyond heat, there are other cost drivers. The ability to precisely maneuver, for hypersonic weapons at least, at very high speeds. And the plasma environment offers a challenging guidance, navigation, and control and communications problem. Now, for our purposes here today, I'm going to focus on three parts of a hypersonic vehicle: a glider, which has no propulsion, a cruiser, which uses scramjets for propulsion, and then each of those requires a solid rocket booster to get them to the initial Mach 5 speed required. Here's a database I've assembled for some historical hypersonic vehicles. Notice in column A there are 19 data points in this database. A long name in column B, a shorter name in column C. In column D, I've made note of what kind of propulsion the vehicle used, excluding their first stage propulsion. Some of them were rockets, some were gliders, which had no propulsion, and there's 3 scramjets in the database. Column E tells us what the first stage was, and the cost for this first stage is not included in the cost numbers that I'll be discussing here today. So for example, the X-15 flew on a B-52. Others flew on various missiles and rocket stages of our airplanes of other types. The initial operating capability date is given in column F, and then the following columns have some of the technical information that we'll see if we can use any of these as cost predictors. So I have dry weight in column G in pounds, Mach number in column H, their length and altitude and range in columns I, J, and K. Column L is a heritage or percent new design factor, which is always pretty important in cost estimating, but here it nulls out because I've assumed that all of these were 100% new design when they were initially developed. Then in column M and N, I have their cost. Now the cost numbers here include the engines, if they had engines, so that the two that do not have engines were X-38 and HL-20, but the rest of the data points include the engines, both in the development and in the T1 or first unit cost, as well as the development and production cost of the hypersonic vehicle itself. There's some other notes at the bottom of the chart here that I won't take the time to go over today. Here's a similar database for 13 solid rocket boosters. And you see their names, their IOC date, their weight, length, diameter, volume, and their costs in the far right-hand side of the chart, RDT and E. In this case, it's average unit cost. And the reason it's average unit cost on this chart, and it was T1 or first unit cost in the previous chart, is that the cost data comes from public domain sources, and they almost always quote the cost for solid rocket boosters for an average cost over however many units were built. So it'll be a little bit more research to research how many were built and back those up the curve to get a theoretical first unit cost. And I didn't go to that trouble for this exploratory presentation here today. All right, here's a scatter plot of the hypersonic vehicles, the first database I showed you. The chart on the left is the development cost, and the chart on the right is their first unit cost. Now, this is both these plots are log terms, logarithm of the development cost and logarithm of the theoretical first unit cost on the vertical axis, and the logarithm of weight, dry weight, on the horizontal axis. Here's a similar scatter plot for the database I showed you for historical solid rocket boosters. The dotted lines on these two plots are a cost model that was reported in the literature a few years ago at an ICEA workshop, as noted at the bottom of the chart. Updated to be $2020 because I'm in $2020. But I wanted to overlay the cost model from that paper onto my solid rocket boosters just as a sanity check. And it looks like they're in family. So that's a good check, I think. Okay, data normalizations, I put everything in $2020 for the hypersonic vehicles. They include the weight and cost and includes engines, except for the ones that did not have engines. Some of the hypersonic vehicles in the database used existing engines. So in that case, I added back the original engine RDT and E cost to make it homogeneous. We want CERs that estimate everything we need, assuming 100% new design. As you go forward in a cost estimate and a cost model I'm going to show you in a few minutes, you can factor that new design down to something less than 100% if you want to, but the database has been normalized to include engines, include the vehicle, all at 100% new design. Some other rough normalizations, the weight and cost of all systems associated with crew was removed. I've listed the crewed vehicles there, X-15, the shuttle orbiter, HL-20, and X-30. So I took out the weight and cost of those systems. The weight and cost of landing gear was also removed. I'm assuming here in this presentation that we're estimating the cost of a hypersonic weapon for the most part. So we're not going to need landing gear, obviously. So I took the weight and cost of landing gear out for those systems mentioned parenthetically there. Fewer normalizations are required for the solid rocket boosters. Boosters are pretty simple. Boosters are boosters. So I really didn't have to do anything to normalize that except the year dollars. All right, I'm going to try to get some indicator variables in the cost model. Indicator variables go by other names such as dummy variables or binary variables. As mentioned, while the weight and cost of crew systems was removed from the historical hypersonic vehicle data for those vehicles that carry crew, I still have to leave that in as an indicator variable because I want to control for the human rating effects on the remaining subsystems. So this human rating variable will obviously be turned off for estimating a planned DoD hypersonic weapon, but it's in there to control for the human cost that would be contaminating the other systems for those systems that did carry crew. Another indicator variable was similarly included to control for the lack of an engine in gliders. Now, this can be flipped to on for scramjet hypersonic vehicles or to off for glider hypersonic vehicles. Now, flipping it on may not fully account for scramjets because you may recall in the database there were only 3 scramjet engines in the database. The rest were rocket engines. So presumably rocket engines may cost less than scramjets. And so in that case, flipping this variable to on may not fully account for scramjets, but it takes the cost in the right direction at least. All right, so here's an example, RDT and E CER for hypersonic vehicles. It's actually the best CER I could get from the database that you saw. So what statistically made it into this cost estimating relationship are the variables weight, Mach number, whether or not it was human rated, and whether or not it had an engine. Those passed the t-test. All of those passed the t-test just okay, except for engine. So if you look down in the bottom right-hand corner of the chart, you'll see the p-value for engines. And those of you who are used to doing regression analysis will note that a 0.275 is really not passing a t-test. Normally you want it to be a 0.05 or lower. You see that the p-value for dry weight, Mach number, and human rating are okay there. They're good. I left engine in because it's important to have that in from a technical perspective. And so even though it doesn't strictly pass the t-test, I left the variable for engine in. Also, you'll notice that it has a very high R squared there, 91.3%. That sounds pretty good, but in fact, this model is overfit. I've got 19 data points and 4 independent variables. So that R squared is being driven by the fact that the model is overfit. I'll say a word about overfitting later. All right, so to save time, I'm not going to show you 3 other CERs that I developed using the exact same process. I developed a T1 CER for the hypersonic vehicles, an RDT and E CER for solid rocket boosters, and an average unit cost CER for solid rocket boosters. So next I'm going to show you a cost model in Excel that implements these 4 CERs. Now in the small print in the chart here, you'll actually see the 4 CERs listed. The first one there for RDT and E is the one that you saw a moment ago. The top table in this cost model is the hypersonic vehicle, either a glider or a cruiser. And the bottom part of the chart is the cost model for solid rocket boosters. So let's look at the top one first. Notice I have in green, the inputs are in green cells. Notice the first input is percent new design. I've set it at 100%. But if you had reason to believe that your hypersonic vehicle, either a glider or a cruiser, had heritage from some previous development, you could lower that number. I've put a variable, I've set the variable for human rated. I put in 0 here because we're assuming we're estimating a weapon system which would not have a crew. So I'm turning the human rating element off. And I chose to say this is a scramjet instead of a glider. So I put a 1 in for the input for is it a scramjet. To keep this unclassified, I've assumed the weight runs for this cruiser from 500 pounds to 1,500 pounds dry weight, as you can see in the other cells there. And then I've assumed that the Mach number ranges from 5 up to 25 in steps of 5. So let's just look at the middle of the table there. I put that 380 in red. So that is the cost in millions of dollars of a hypersonic vehicle that weighs 1,000 pounds and has a top speed of Mach 15. The T1 cost, the first unit production cost of that same 1,000 pound vehicle going Mach 15 would be that red $42.3 million in the center of the second little table there. All right, now similar process for the solid rocket booster down below, but it's a lot easier because as it turns out, the only variable I could get into the solid rocket booster cost model was weight. So again, I've assumed 100% new design for the solid rocket booster, and then I've let the weight vary from 500 to 2,500 pounds. That includes propellant. So we see that, for example, a 1,500 pound solid rocket booster would be predicted by this cost model to have a development cost of $70 million. And it would be predicted to have an average unit recurring cost of that $1.3 million. It's in red towards the bottom of the chart. So in the bottom right-hand corner of this table, I've collected the red numbers and total them up. So for the hypersonic vehicle element, we're getting a development cost of 380. For the T1, a $42 million number for a total of $423 million. The development cost for the solid rocket booster in this example here is $70 million, and the average unit cost is 1.3. So we're looking at a total system cost here of around $500 million in this rather fictitious example. I said I was going to say something about overfitting. So the CER in this hypersonic vehicle CER in this presentation is overfit. An overfit model is one that's too complicated, has too many variables for the number of data points you have. So an overfit model can cause the regression coefficients to be misleading. There's a rule of thumb, there's lots of rules of thumb, but one rule of thumb that I tend to use is that you need to have at least 10 data points per independent variable in your CER. Now, some statisticians say even more than 10, 20 or more. But obviously I don't have that many for the 4 variables that I have in my CER: weight, Mach number, human rated, and engine. I would need 40 data points, okay? And obviously I'm not going to find 40 historical data points on hypersonic vehicles. But from an engineering point of view, it's desirable to be able to generate cost sensitivities to these key variables. So I've left them in. I'm living with the overfit issue. Now, overfitting can be addressed a number of ways. You can find more data. That's not likely for hypersonic vehicles, but perhaps for solid rocket boosters. You can compare the estimates to estimates coming from CERs we've already developed with these same databases, but in which we did not crowd in too many variables, and see if you get anomalous or funny looking results. You can compare your results with to ancillary models that I've mentioned in this package, that paper from the ICEA workshop several years ago. But all this is beyond the scope of today's presentation. So some concluding remarks. This presentation has admittedly treated the subject of hypersonic vehicle cost at a very superficial level. But now, if you're in the business of developing or managing the development of a hypersonic vehicle, we at Galrath have much more detailed and accurate cost models. We have a series of parametric cost models called SEER-H and SEER-SIM, which estimates hardware and software respectively. SEER-H operates at the hardware major assembly level of design. So if you've got a hypersonic vehicle design that goes down to the major assembly level, SEER-H could be readily used to estimate its cost. CRSIM is a software model that operates at the CSCI level and works off of slot counts, software lines of code. So contact me if you're interested in learning more about how Galarath cost models can improve the accuracy of the estimates that you may be making of hypersonic vehicles. A final word, Galarath is a 75-person company. We're dedicated to providing our customers best practice cost analysis. I've listed some of our decision-making capabilities there in that list. You can gaze down through that. Our web address is at the bottom of the chart, and I'm repeating my email address there. So thank you very much.